Hi there. A little trouble with the video, so this last bit will be separate. Right, I just wanted to finish up our discussion and then do a quick example, okay? 1 second. There we are. So we had just talked about rare earth metals and found that because of electrons in unfilled shells deep within the atom, these atoms tend to have a magnetic moment, and they retain their atomic-like magnetic moments even when they're combined into metals or into molecules. Transition metals are somewhat similar. In transition metals, the 3D or 4D shells also partially fill with electrons. And so these electrons in these partially full shells are likewise shielded from the environment by electrons in outer orbitals. Only now the shielding is only partial. And in this case, what tends to happen is that the spin part of the angular momentum remains atomic-like, but the orbital part of the angular momentum tends to be quenched when the atoms make bonds with other atoms in molecules and solids, so that the magnetic moment of the transition metal atoms ends up being dominated by the spin contribution, and the orbital contribution isn't important. Okay? Here I wanted to do an example. I wanted to work out the maximum magnetization in iron based on what we've learned. All right. So here's the idea. In iron, the iron atoms carry a magnetic moment. And the magnitude of the magnetic moment is approximately 2 Bohr magnetons per atom. Okay? That means that if we combine them into a solid, the solid can be magnetized, but the maximum possible magnetization will occur when all those magnetic moments line up. So the maximum magnetization will occur when the total magnetic moment is equal to the density of atoms times the magnetic moment for a single atom, or 2 mu b n over b. Okay? And for iron, then we have a maximum magnetization, which is 2 times 9.27 times 10 to the minus 24 joules per Tesla, times the density of atoms, which is approximately 8 times 10 to the 28 atoms per meter cubed. And combining these gives a value, and you can see it's a large value. It's about 1.5 times 10 to the 6 joules per meter cubed. So that should be the maximum magnetization of iron. It looks like a big number, and we can see how big it is if we use this to figure out the magnetic field that you should obtain inside a piece of fully magnetized iron. So if all the magnetic moments line up, then this should produce a strong magnetic field, and we can estimate how large that is. So then the magnetic field should be mu naught times H plus M. And we're assuming here that we don't need an external field. We don't need an H field to produce this magnetization. It's just sitting there fully magnetized. And so the total field will be mu naught times M. And so this will be 4 pi times 10 to the minus 7 times 1.5 times 10 to the 6, or approximately 1.9 Tesla. So inside of a fully magnetized piece of iron, we'd have a magnetic field of almost 2 Tesla, which is a very large magnetic field. It's essentially about the strongest magnetic fields that can be created in the laboratory without using superconducting magnets. Okay, so very large indeed. And this is completely attainable because, in fact, iron is a ferromagnet, and the spins in iron actually like to line up. So we don't have to do very much extra work to fully magnetize a piece of iron. All right, let's stop here.